Software development often begins with a specific engineering trap, the rush to code. Developers immediately begin typing raw programming logic without any prior planning. This creates a deceptive sense of progress. While writing lines of code feels productive, jumping straight into the keyboard without a strategy produces a chaotic, unorganized internal structure. Building this way is like mapping a massive pitch-black cave using only a small flashlight. You see the jagged rocks right in front of you, but the shape of the overall cavern remains unknown. Eventually, the project hits a point of no return. Once the code reaches a certain volume, it becomes impossible to accurately assess its stability or quality because the foundational structure was never defined. Formal software design acts as the bridge here. It serves as a translator, turning abstract human requirements into the rigid mathematical logic that a machine can actually execute. This phase builds in the architectural stability, usability, and long-term value that basic functionality alone cannot provide. Skipping this step makes a product brittle by default. A formal design is the most effective method for managing the complexity of a digital system before it spins out of control. Successful design begins at the lowest level. Before any features or user interfaces are sketched, an engineer must first define the architecture of the data. This starts with the data object. This crystal represents the information manipulated, broken down into specific properties, like a user's ID. These objects are mapped together using strict relational rules. This web of connections defines how information flows, ensuring every data point has a logical home. If the foundation is weak, the entire application will fracture. Flaws in the data structure will eventually manifest as bugs in the features and screens that sit on top of it. Data architecture is the non-negotiable skeleton of the software. If this skeleton is deformed, no amount of visual polish can make the application functional. Once the data is organized, the process moves up to the structural framing, the software architecture. This is the master plan for how the system as a whole functions. To manage complexity, engineers use separation of concerns. They take one massive computational problem and slice it into dozens of isolated modules that can be built and tested independently. When designing these modules, engineers don't start from scratch. They rely on established design patterns, blueprints created by past engineers to solve recurring challenges. By using historical templates, developers ensure structural integrity from day one. Utilizing these patterns alongside a separated architecture prevents developers from wasting time on solved problems, allowing them to focus on the unique aspects of their project. With the macro architecture set, the focus shifts to the microscopic mechanics. This is component-level design. Components are guided by cohesion, doing exactly one thing flawlessly. They also need low coupling, interacting with other parts only as necessary. High coupling is dangerous. If tightly linked, a small bug causes a ripple effect breaking the other, leading to system-wide failure. To prevent this, developers use a discipline called refactoring. They constantly optimize the internal logic of a component to keep it clean, without changing what the user sees on the screen. Maintaining high cohesion and low coupling ensures that when a bug does appear, it remains isolated within a single component, instead of crashing the entire application. This finalized design model represents the accumulation of every data strategy and architectural decision made during the process. Because this model exists as a blueprint, it can be stress-tested and logically reviewed for errors before a single line of actual code is ever written. This replaces the blind guessing of the rush to code with a verifiable technical map. The cost difference is massive. Catching a structural error on a design blueprint costs almost nothing, but fixing that same flaw after it has been deployed in live code can cost millions. This structured approach eliminates the guesswork of development. By resolving conflicts on paper first, engineers turn complex ideas into reliable software that survives the move from theory to execution.